and welcome. In our last lecture, we had started with the discussion of gravimetry and we had seen what are the conditions required for a perfect precipitate, what is a colloid, how can the formation of a colloid result in loss of precipitate, and what are the various sources of error which can occur in gravimetry resulting in the loss of precipitate. So, the first source of error which we studied earlier was peptization, and peptization which needs to be prevented, peptization which is the passing of a precipitate into the colloidal form which needs to be prevented. Then the second source of error which we were discussing was supersaturation, and which needs to be avoided, which is a metastable state, so it can be avoided easily. The third source of error which we have started is, before that we were discussing the supersaturation, or how can it be reduced. Supersaturation, as we have discussed, is a metastable state of equilibrium and it can be easily reduced to avoid errors in gravimetry, and that supersaturation can be reduced by dilute solutions and by using hot solutions in gravimetry. So, hot solutions reduce supersaturation in many ways, that is by increasing the solubility of a precipitate. Then a constant change which occurs during heating of a solution, which helps to disturb the metastable state of supersaturation of equilibrium. The constant stirring of the solution which needs to be carried out, which helps to disturb the metastable state. Then the slow addition of the precipitating agent. By adding the precipitating agent slowly, the benefit which occurs is that the initial particle formed is very small, which acts as a nuclei for the formation or deposition of other particles, and hence the formation of a large particle. And since large particles are formed, then those particles or the precipitate does not pass through the filtering medium. So, the addition of the precipitating agent should be done very slowly with the help of a dropper. The adjustment of the alkalinity or acidity of the solution or the medium can be done to increase the solubility of the precipitate in hot solutions, so that they can be easily precipitated out in cold. Another way in which error in gravimetry can be reduced is by precipitation from homogeneous solutions. Here, the precipitating agent is generated from within the solution at about the same rate as the rate of precipitate formation. That means no external precipitating agent is added. Instead, the precipitating agent is created from within the solution. As you can see in the example below, NH2SO3H along with water gives ammonium ions and H plus ions and sulfate ions. The sulfate ions which are being formed within the solution combine with barium ions to form barium sulfate precipitate. So, in a solution of barium chloride, if we add the solution of ammonium sulfonilic acid, or as we know simply sulfonilic acid, then it helps to generate sulfate ions within the solution. The sulfate ions which are generated within the solution are combining with the barium ions to form barium sulfate precipitate. So, there is no precipitating agent added from outside, or as we say, there is no external precipitating agent, but the precipitating agent, which is the sulfate ions, is being produced within the solution and is forming a precipitate with the barium ions. This avoids supersaturation, as the sulfate ion which is being produced is in the solution and is immediately reacting with barium ions to form barium sulfate. So, it gives no time for supersaturation to occur within the solution, because the rate at which sulfate ions are being formed is the similar rate at which barium sulfate precipitate is being formed. Some other sources of error in gravimetry are co-precipitation. Co-precipitation is the contamination of a precipitate by substances normally soluble in the mother liquor during precipitation. So, when precipitation is occurring, then it is quite possible there are some impurities which are already present in the solution or which accidentally are present on the glass rod or in the apparatus, the beaker in which the precipitation is being carried out, and the precipitates which are now being formed can include those precipitates, or those precipitates can be contaminated by the impurities which are already present in the mother liquor but are in the soluble form in the mother liquor. So, this takes place in two ways. Firstly is by surface adsorption. Surface adsorption takes place on particles of ions or undissociated weak electrolytes. For example, adsorption of H2S on metal sulfide precipitates. H2S is a precipitating agent. It can precipitate certain metal ions like arsenic or copper, which can form their sulfides, and during the formation of arsenic sulfides, for example, arsenic sulfide precipitate or copper sulfide precipitate or zinc sulfide precipitate for that matter, H2S particles get adsorbed on these precipitates and the initial stage only. That means when the first particle of the precipitate has been formed, H2S tends to get adsorbed on the surface, and when the next particle gets attached to the previous particle, then this H2S molecule gets occluded or entrapped in the required precipitate. This results in the error in gravimetric analysis. So, occlusion of contaminants while bigger crystals are being formed takes place. The contaminants are adsorbed first by the small crystals, and as these small crystals aggregate to form bigger ones, the impurities are trapped inside the crystal structure, as we have just discussed. Co-precipitation can be reduced by making the particles regular in shape, since irregular particles have more surfaces exposed for the adsorption of impurities. So, if a particle is spherical or circular, and if a particle is square shaped or star shaped or any other irregular shape, then an irregular shaped particle will have more surfaces exposed, and once an irregular particle has more surfaces exposed, then more impurities can get adsorbed on the exposed surfaces. So, to reduce that, the particles need to be regular in shape. So, making the particles dense so that no spaces are left between them are also reducing chances of co-precipitation. So, the requirement for reducing co-precipitation is that the particles should be regular in shape and the particles should be dense. Dense in the sense there are no interstitial spaces left between them. For carrying out this regularity in shape and also for making the particles dense, digestion or aging of the precipitate is carried out. In this, either the precipitate is left overnight or is heated on a steam bath for 30 minutes. Another source of error in gravimetry is post precipitation, and as by the word post, that means after the formation of the required precipitate. So, the contamination of the required precipitate by other substances after the process of precipitation is called post precipitation. For example, in the precipitation of calcium ions as calcium oxalate, if some magnesium ions are also present, then they will also be precipitated as magnesium oxalate and will form a layer on the calcium precipitate, thus causing error. So, if calcium oxalate precipitates needs to be formed, if we have a solution of calcium ions, we have to estimate how many calcium ions are there in the solution, or for that matter, if we take a simple example of water, tap water, which is usually hard water, and we have to estimate how much amount of calcium ions are present by gravimetry. Then we precipitate the calcium ions as calcium oxalate by adding oxalic acid and by adding an electrolyte. But as we know, hard water also contains magnesium ions, so magnesium ions will also be present. They will also precipitate out as magnesium oxalate and will tend to form a precipitate or a layer on the initially formed calcium oxalate precipitates. This may cause error in gravimetric analysis. Co-precipitation decreases on digestion, whereas post-precipitation increases on digestion. As we have just seen, digestion is carried out by keeping the precipitates overnight or heating them on a water bath or steam bath for around half an hour. So, if we keep the precipitates overnight, then it increases the risk of post-precipitation, but co-precipitation decreases. Digestion is helpful for improving the quality of the precipitate apart from reducing co-precipitation, but it is not helpful for amorphous precipitates like ferric hydroxide. It is only useful for crystalline precipitates. So, to reduce errors due to co-precipitation and post-precipitation, optimum conditions have to be chosen. The general conditions hold for most kind of precipitations except a few. For example, zinc and magnesium are precipitated as their ammonium phosphates in cold solutions. So, what do we know is in this case that co-precipitation and post-precipitation are sources of error in gravimetry, and to reduce these sources of error, certain conditions have to be chosen so that the precipitates which are obtained in gravimetric analysis are having the exact weight which needs to be calculated. And general conditions are applicable to all precipitates. General conditions which we have just discussed are applicable to all kind of precipitates. However, in case of zinc and magnesium, they are precipitated as their ammonium phosphates in cold solutions. Generally, we have seen that precipitation needs to be carried out in hot solutions. First, the solution should be hot to avoid any kind of supersaturation or any kind of error in gravimetry, but certain ions like zinc and magnesium, they are totally soluble in hot solutions and they will not precipitate out in cold solutions even if the solution is slightly warm. So, they need to be precipitated in their cold solutions only, and that is the way to reduce error in gravimetry. If we consider nickel, for example, to be estimated in a particular solution as a nickel DMG complex, it is the most common complex of nickel which can be easily precipitated out. Nickel can form a very good complex with DMG, which is called dimethyl glyoxime, and it gives very good thick red colored precipitates which can be filtered out and estimated. So, in order to estimate nickel ions in a solution gravimetrically, they are precipitated as the nickel DMG complex. DMG or dimethyl glyoxime is an organic precipitant or as we say precipitating agent, which precipitates nickel ions in alkaline medium. So, for the precipitation of any particular metal ion, there is a need of a particular medium which is either alkaline or which is either acidic. This is a reaction which is showing the combination of nickel with glyoxime, DMG, dimethyl glyoxime, and this is the complex formed nickel dimethyl glyoxime complex which is red in color, and this complexation takes place in alkaline medium. So, the conditions which are required for a good precipitate to be formed, or as we say the conditions required for precipitation include dilute solutions, which we have already discussed, as a solution should be dilute because they give more space for the original particle to be formed, and other particles to occlude on it. Hot solutions are important for precipitation. Constant stirring is required to disturb the metastable state of supersaturation. Slow addition of the precipitating agent is needed so that if the precipitates are formed slowly, then the size of the particles will be larger and they will not pass through the filtering medium. Small excess of reagent needs to be added. The reagent, that means the precipitating reagent we are talking about here. A very small excess needs to be added so that the equilibrium is shifting towards the unionized salt and the precipitate is forming easily. The medium needs to be adjusted to a suitable pH, whether acidic or alkaline, depending upon the conditions or the metal ion or the precipitating agent which are being used. The addition of an electrolyte is again important to prevent peptidization, as we have already discussed. Digestion of a precipitate is important to reduce co-precipitation, but of course it slightly increases post-precipitation. But to decrease post-precipitation also there are a number of other ways which we have already discussed. Electrolyte is added in wash solution to reduce peptidization. This point also we have already discussed. Peptidization is the passing of a precipitate into the colloidal form, which needs to be avoided, and for that the wash solution which is used for washing the precipitate obtained needs to contain an electrolyte so that the concentration of the wash solution does not fall, the electrolyte concentration does not fall below the coagulation value. The nature of the precipitate to decide the filtering medium. So if the precipitates are very small in size, then accordingly the filtering medium needs to be decided whether it should be simply a Wattmann paper, Wattmann 42 filter paper, Wattmann number 40 filter paper. This is just difference of the pore sizes, or if the precipitates are needed to be filtered through sintered glass crucible where the filtering disc has even a smaller pore size. Once the precipitates have been formed, there is a need of washing the precipitate, and it is done to remove any soluble impurities adhering to the surface of the required precipitate. Any soluble impurities, which tells us that those impurities which are soluble in the electrolytic solution of water, they can be removed if they are soluble in water. For this purpose, that is for the washing of the precipitate, wash solutions which are used need to be specific, need to be having certain properties. Electrolyte should be added to these wash solutions to reduce chances of peptidization. Electrolyte should not react chemically with the precipitate. It should be volatile, that is, it should get removed during heating or ignition of the precipitate. The electrolyte which is added to water to increase the ionic strength of water should not chemically react with the precipitate. The precipitate which has been produced should be unreactive with the electrolyte. It should be volatile, and generally for that purpose the electrolytes which are added are generally hydrochloric acid and or chloride salts, because all chloride salts are highly volatile. For example, if we need to precipitate barium as barium sulfate, then we initially choose a solution of barium chloride. To that we add an electrolyte which is hydrochloric acid, then after that we heat it on dilution, and then we add sulfuric acid which precipitates barium as barium sulfate. Then this barium sulfate precipitate which is obtained is washed with a solution of hydrochloric acid in water, and that hydrochloric acid behaves as an electrolyte and it is highly volatile. It will, the chloride salts which are now attaching to the precipitate or which are present in the solution, upon filtering will be removed once the precipitate is heated or ignited. And the example which is given over here is silver chloride precipitate is washed with dilute nitric acid again. In this case, dilute nitric acid again is highly volatile. NO2 will be formed when the silver chloride precipitate is heated. Wash solution should be such that the solubility of the precipitate in the wash solution should be minimum. This is done by keeping one ion in common with the precipitate. For example, ammonium oxalate solution is used to wash calcium oxalate precipitate. So there, in this case, oxalate ion is common, and since one ion is common in the wash solution, then in this case the wash solution does not dissolve the precipitate, and the solubility of the precipitate in the wash solution is minimum. Ammonium salts are also generally preferred because they are highly volatile. Just like chloride salts are volatile, so ammonium salts are also preferred in a similar manner. The wash solution should be such that it should not cause the hydrolysis of the salt of a weak acid or a weak base. The wash solution, for example, in this case, ammonia solution is used to wash the precipitate of magnesium ammonium phosphate, which gives basic solution on hydrolysis. So the wash solution should not cause the hydrolysis of a salt of a weak acid or a weak base. The reducing substance needs to be added to wash solutions in case where the precipitate is prone to oxidation. In that case, the precipitate will not get oxidized once it is washed with a reducing substance. Wash solution should be used as little as possible or in as minimum quantity as possible, since otherwise peptization might occur. And we have discussed already what is peptization, which is passing of the precipitate into the colloidal form, and if the wash solution which is used is simply water, then peptization may occur, and if the wash solution is used in large quantities, then also peptization may occur. Also, the washing should be done by adding the wash solution in small lots rather than one big lot. The addition of one big lot of the washing solution might result again in the passing of the precipitate into the colloidal form. Warm wash solutions can be used to increase the speed of filtration. Heating or ignition of the precipitate is done after the precipitate have been washed as required, depending upon the nature of the precipitate. So what we have discussed till now is the various steps which are involved in gravimetry, and the ultimate step, which is the washing of the precipitate before it needs to be filtered out and before the heating or the ignition of the precipitate is carried out. Heating or the ignition, which is the final stage of gravimetry, wherein the precipitate which is produced is removed of all the absorbed moisture, water of constitution or water of crystallization, and there are certain requirements for washing of the precipitate and certain requirements for the wash solution which is also used, which we have discussed. And after washing of the precipitate, when ignition or heating is carried out, it gives us the required precipitate which can be weighed, and the amount of the metal ion in the solution can be determined by a series of calculations. Thank you.